Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about random variables and expected value. This is a topic that's a little bit of math, a little bit of statistics. It's really an extension of a lot of the probability things we've talked about before. So a random variable is just associating a variable with some experiment that has a numerical outcome, right? So there's lots of simple examples for this. So we could think of rolling a dice, a fair die, and you look at, okay, do I get 1, 2, 3, 4, 5, or 6? Of course, all of those have different probabilities associated with them, and so that's why it would be talked about as a random variable. It will take on a set value, but not until after the experiment is done or something like that. Right? This could also be the number of heads in 5 coin tosses. So the key thing here is that we have a numerical outcome, right? So we're not thinking of like, okay, who wins the game? Is it team A or B? We want to have some numbers associated with it. You could associate numbers to those types of things. So for example, right, if you wanted to measure how happy somebody was, right? If their favorite team won, maybe you would have a higher number. If their least favorite team won, maybe you would have a lower number or a negative number. There's a lot of ways to quantify things, but specifically here, we're going to be talking about outcomes that are numerical, and that's the easiest way to start getting your head around this idea of a random variable. So in terms of the mathematics, understanding what a kind of random variable is, right? Like I mentioned, we need to talk about associating those numerical outcomes with the probabilities. And this is typically what's done in what's called a probability mass function. So what we're doing with a probability mass function, you can think of this as a function more formally, but because we have a set number of outcomes, it's oftentimes easiest to think of that function as a table of values, right? So we only have a couple of values here. So on one side, we're going to have k. I'm going to use k to denote the different possibilities for this random variable. And if we're rolling a fair die, this one's pretty simple, right? So our first example of this is, of course, going to be pretty simple there. We have 6 possible outcomes in this case, right? You either get a 1, 2, 3, 4, 5, or 6. And then we want to associate it, as I mentioned, the probability that that value is actually going to happen. So our other portion of the table is the probability that that random variable x is equal to that specific k value there. So this one, as mentioned, is pretty simple because you have a 1/6 chance of getting a 1. You have a 1/6 chance of getting a 2, right? Assuming we have a fair die, 1/6 chance for 3, etc. Right? So we have a 1/6 chance for all of these 6 different outcomes there. If you study these more formally, right, you'll start noticing some properties. Of course, all of our probabilities here have to add up to 1 because that's describing all of the possible outcomes here. All right, so here's our kind of fair die example where we're rolling the die and we look at the different outcomes there. Now, these things don't have to be quite as simple. Right, our other example we looked at was, okay, we have a fair coin, we're flipping it 5 times. What is the number of heads that we get there? Right, so this one is a little bit more complicated as far as the numbers are concerned, but in either case, our table is going to have a fairly similar look to the other one. We have our k, what are the different possibilities that are happening? Again, this has 6 outcomes, so don't be kind of confused by the fact that we're flipping the coin 5 times. because, right, you still can get 0 heads all the way up to 5 heads in this case. So we have 0, 1, 2, 3, 4, 5. And we want to kind of always calculate the probability that our random variable is equal to that specific value there. Now, we can sometimes do these in a little bit more of a kind of quick manner as well. And right, sometimes you will not see the whole table written out. I am going to write the whole table out, but off to the side here, let's just do it in general, and then I can fill in the specific values for the table, right? So if we look at here the probability that y is equal to k, this is a probability question we've kind of looked at before, right? So for example, our denominator is just going to be 2 to the 5th. We have a fair coin. We're flipping it 5 times. Every time you either get heads or tails. So we have a 2 to the 5th, or 32 on the bottom. That is our total number of outcomes there. Now, what about the number of heads? Well, we have 5 flips. So we have kind of 5 slots for our heads. Some of them can be heads, the rest can be tails. This should be reminding us of a combination, right? We're choosing where the heads go, the rest of the slots are for the tails. So we could write out a formula here. So this kind of is a good example to see how in certain scenarios you can have kind of a more general formula like a function you might normally see, but we could also summarize things in a table. Right, my formula to the side here isn't totally complete. We have to say what values of k make sense for that. But today I really want to focus on our table as the way of thinking about the PMF. So quick calculations here. 5 choose 0 is 1, so we have 1 over 32. 5 choose 1 is 5, so we have 5 over 32. 5 choose 2 is 10. So we have 10 over 32. And then if you remember, we have some symmetry in these binomial coefficients. So our same pattern is going to continue just in reverse for the other 3 numbers there as well. Right? And I do want to stress, let me highlight that really quickly here at the end. It is important that we have a fair coin. Things are going to be a little bit different if we didn't have a fair coin, but the idea is still similar in that case. So, right, PMF for this random variable describes all the possible outcomes and then all of the probabilities of those things happen. Let's talk now about expected value. This is a little bit more now of the real power of a random variable, right? If you're just going to say, okay, what are the different probabilities? That's a probability question. Why do we care about being careful about this random variable or stuff, right? Why don't you just talk about, okay, what's the outcome of the experiment? What's the probability that that happened? We want to start having ways to study the whole random variable. And the first of those ways, we'll see some more probably in a later video, is expected value. So the expected value is in a sense the weighted average of all the possible outcomes kind of weighted by their probability. So in a sense, this is kind of what you expect to happen on average over a long period of time. There's a lot of statistics connecting those two ideas. Right? This is purely a kind of mathematical formula here, right? So our formula is, right, you take each output times the probability of it happening and you add all of those up. So this is easiest in an example we'll see in a second. But the idea is, and you can do the statistics, there's some laws about this. In general, it kind of means on average what happens if you do this a bunch of times in that case, right? If you kind of roll a die where you have 1 through 6, it makes intuitive sense, and this is what the expected value would tell us, right? If we had our x is the roll the fair die, right? We can almost just do that one intuitively. So if x is roll the fair die, right? The number on a fair die, you're going to have on average, right, the number in the middle, right? You're not going to ever get 3.5, but, right, on average here, we would kind of expect the number we would get is 3.5 in this case, right? And so you can double check that with the calculation we're going to do on the next page for a more complicated random variable, but this is the rough idea of that expected value. So let's see it in action here. So we're just going to give you a PMF here. So we have a random variable. There are 4 outcomes. You can either have 1, 2, 3, or 4. These probabilities are a half, a fourth, an eighth, and an eighth. So again, these 4 probabilities add up to 1. But let's kind of go through the procedure of calculating this expected value in this case. Right, so what I said we do here is you take each value, you multiply it by the probability, and so we have a half. Then we have 2 times a fourth is a half. Then 3 times 1/8, this is going to be 3/8 here as well. Whoops, so 3/8 there. And then 4 times an eighth, this is 1/2 here too. So, right, we have our kind of amounts discounted or weighted by their probabilities in this case. And now we go through, right, so after we have all of these values, we add all of these values up here. So we take all of our values and we add them up one by one. So we have 1/2 plus 1/2 plus 3/8 plus 1/2 there. So we have, right, 1.5. So that is like 12/8 plus 3/8. So we have 15/8 in this case. So this is our expected value of x for this problem. So expected value of x here is equal to 15/8 in this case. So, right, this is in a sense your expected amount you could have there, right? So it's a little less than 2, right? You might normally say, okay, well, we have 1, 2, 3, 4. Why is the expected value not like 2.5 or something? But this is where the probabilities come into play, right? We know that 1 is the most likely, a half is the next most likely. So you're more likely to get these smaller numbers, and that's why our expected value on average, we're going to have a lesser value in this case. Now let's look at one final example. This is, in a sense, kind of a made-up example, but is a little closer to something you might see in the real world. Let's say we have a carnival game, and you roll a large die, right? Suppose it's 1 through 6, it's a fair die, right, at this carnival, and some different things kind of happen there, right? So if you get a 1, you win a grand prize of $12 in this case. All right, so let me kind of start keeping track of, in what will be a PMF, we can kind of start keeping track of the different probabilities of stuff that could happen in this case. So let's say we have our different winning values here. So we have our kind of k, I'll stick with that value, and whatever our random variable is, let's just call it x to be consistent. We have the probability of winning that there. Now, to be careful here, we want to make sure we're keeping track of the money, right? The actual thing here is talking about our prizes we could be winning, what might we pay to play this game. We'll get back to that after we do this. But, right, let me think of the outcomes here are 12. You could win $12. A roll of 6 wins a prize of $2. Or you could win nothing, of course. So our three money amounts are $12, $2, and $0. These probabilities, of course, come from the rolls, right? You get a 1, so that is a 1/6 chance you win $12. You get a 2, that is another 1/6 chance you could win $2. And then the other times, the other 4/6 or the other 2/3 times, you actually win nothing in that case there. So, practicing our expected value a little bit here. The expected value of x then, let me write this out. We have $12, but you win that with a probability of 1/6. And then you could win $2 with a probability of 1/6. Let me write it out for completeness, right? Then you could win $0 with a probability of 2/3. That, of course, doesn't change this number here at all. But our expected value then is 2 plus 1/3, right? So we have here, maybe let's do even approximately 2.33 in this case. So it's 2 and 1/3 in this scenario. But we're thinking of money now, right? So our expected value is approximately $2.33 in this case there. Now, in fact, we've just answered the question, right? So let me kind of explain this a little bit. This is starting to tell us the power or the real world examples of stuff like expected value, right? What does it mean to be fair, right? A fair game might be something where your expected winnings is what you would pay to play this game, right? So we would kind of, let me just say we could pay up to or less than or equal to kind of $2.33 to play this game here. In fact, you should expect to kind of win money if you pay less than $2.33 there. Because, right, you expect to win that amount. You might not win it every time, right? 2/3 of the chance you win nothing. But, right, 1/6 of the time you win $12. So, on average, you're going to win $2.33, right? Or $2.33. So if we're talking about this fair price, right, you don't want to be losing money. When we say a fair price, we really kind of mean I don't want to be losing money if I'm going to be playing this game, right? In reality, in the real world, you would pay more than this. Otherwise, the person putting on the carnival game would not want to, right, put on the game. So we're not really talking from the business end. We're talking about it from the personal end, right? You would pay less than $2.33 and then expect to, right, either win money or break even playing this game there. So you start to see now some of the kind of real world applications, right? This is how some gambling games are priced. Of course, in the casinos, then the casino is the one winning money, right? If you are doing insurance, this is the same type of thing, right? You might pay an insurance premium, right? Of course, for the insurance company, they want to, as an expected value, make money on what you're paying. Does that mean every time they kind of make money on every single person? No, because if somebody has a bad accident, they might have to pay out a lot of money, but on average, they're hoping to make money. So we start to see how this expected value could come into play in business and in kind of games and in other mathematical applications as well. Right, and this is starting to get into statistics then a little bit more. So we'll probably revisit this in a future video. But right, expected value by itself has a lot of interesting applications and has a lot of interesting problems to think about that way too. That's it for this Thursday Tidbit. Check back each week for another Thursday Tidbit. And if you're looking for some more practice problems, some more ways to kind of connect with the community, check out the Zoom International Math League at ziml.areteam.org. Goodbye, everyone.